Hello again, physics friends. We're back, and we're going to now look very closely at the first of the three consequences of relativity. We've already seen this in when we did the kind of appetizer of relativity. We saw that events that are simultaneous in one frame are not necessarily simultaneous in the other frame. We call that the relativity of simultaneity. Today we're just going to outline what the three main consequences of relativity are, and then we're going to dive deeply into the first one. So this is a longish video that involves some derivations. So hang in there as we proceed. Now, as a reminder, we know that there are two main postulates of special relativity: the principle of relativity and the constancy of the speed of light. And when we say the three consequences of relativity, what we mean is if we take those two pillars or those two postulates as given, what are the three main effects in relativity that differ from kind of the classical picture? And there are three. Okay, the first one is relativity of simultaneity, which we've already encountered. Relativity of simultaneity. Although going forward, we're going to call this the rear clock set ahead, or RCA for short. And that's synonymous with relativity of simultaneity. So we'll say RCA, aka relativity of simultaneity. That's the first one. The second one is time dilation. And the third one is length contraction. Okay. Now, one way to remember time dilation is by the kind of mnemonic, a moving clock ticks less. And one way to remember length contraction is that a moving rod or object of any kind is short. And for relativity of simultaneity, the mnemonic is the rear clock is set ahead. So you can think of RCA as the mnemonic for relativity of simultaneity. So today in this video, we're going to dive really deep into this rear clock set ahead. So we're going to focus entirely on that one for today, and we're going to derive the effect. We already know that events are simultaneous for Alice are not simultaneous for Bob, but today we're actually going to derive how different in time, what is the difference in time between those events for Bob, and what are the consequences for the clocks that are moving. So with that, let's get started. So let's work with the relativity of simultaneity. Last time when we talked about this topic, we gave a qualitative explanation for why events that were simultaneous for Alice on the moving train were not simultaneous for Bob, who stood at rest on the ground. And just as a reminder, the critical piece of information here, right, was that, or the setup of the problem is we had a train, and in the train frame, there was this laser or light located in the middle of the train, midway between the two end walls. And at a single instant of time, two photons were launched from the midpoint, and they traveled to the ends. Because each photon was traveling at the speed of light, and meaning the same speed as each other, and because the photons had to travel the same distance, namely half of the length of the car, we reasoned that those photons would arrive at the walls at the same time. Okay. We also found, though, that from Bob's point of view on the ground, those photons did not arrive at the same time, and the reason for that is that the forward wall was running away from the photons, whereas the back wall was running towards the photons. So the gap between the photon and the rear wall closed faster than the gap between the other photon and the front wall. So the rear photon arrived first as measured by Bob, although they arrived at the same time as measured by Alice. So we're going to make a slight modification to this scenario, and that modification is the following. Instead of putting the light in the middle of the train, we're going to put the light to one side, closer to the front wall. okay? And the effect of that is that in Alice's frame, what we now know is that the photon traveling to the right will get to the front wall before the photon traveling to the left will get to the rear wall. And that's just because it has a shorter distance to travel, okay? Now we're going to choose the exact location of the light source so that although these events of the photon arrivals are not simultaneous for Alice and the train frame, they are simultaneous for Bob in the ground frame. So we're going to tune the location just right to make that happen. I'll explain how we know exactly where to put that light source for the events to be simultaneous for Bob in just a minute. But for the time being, let's introduce the diagram in the ground frame. Okay. So as with all of our diagrams, we're going to be really explicit that this picture is in a specific frame, in this case, ground frame, in which Bob is at rest, but the train and Alice are moving. So actually, let me even draw Alice in here. Right? She's at rest on the train, but she and the light bulb and the train are all moving to the right. Remember, every photon, no matter what frame of reference you're in, is always going to be traveling at the speed of light. Okay. So what does this mean? Well, it means that from the first snapshot diagram to the second, the photons will have traveled the same distance as each other. Okay. So if I draw this green dashed line vertically locating where the light source used to be, then both of these photons have to be equal distant from that light source. Okay, so I'm going to put two little tick marks here, and that just indicates that those two line segments are equal in length. And I know that they're not only equal in length, but they're equal to the speed of light times the time interval between these two diagrams, because distance traveled by the photon is equal to one of those purple line segments lengths, and that distance is speed times time interval. Okay, so we could actually label this distance as c times delta t, and I'm going to put a little tick or a prime on the t, and we're going to call, the reason for that is that the ground frame we're going to call the primed frame. Okay, what does the primed frame mean? Well, that just means that quantities that are measured in this frame will give a little tick. So for example, the length of the train used to be capital L, right? L over 2 plus L over 2, capital L. We're actually going to be really explicit when we label the length of the train, and we're not going to label it capital L, we're going to label it capital L prime. And you might say, why do we have to make that distinction? And the answer, we're going to see quite soon, is quite surprising actually. But we're going to find that L prime is smaller than L, that objects that are moving at high speeds are shorter than the same object when at rest. So although the train you might think of as having a constant length, in fact, the length of the train depends on the frame of reference that you measure the train in. So we're going to recognize that the train length might in general be different by giving it a different symbol, L prime, instead of L. Okay, so we have most of the setup in place now, and I just want to reiterate why we're doing all of this in the first place, right? Our goal is to make a quantitative statement about the relativity of simultaneity. In other words, not just that two events are not simultaneous, but we want to know how far apart in time are they? What is the time interval between when one event happens and the next happens, given that they're simultaneous in another frame, okay? So we need to actually do some calculations and some derivations here. So this is going to be a quantitative calculation. And before we do anything with equations, we just want to make sure that we understand the situation. So that's what talking through all of these and drawing all these diagrams is about. And secondly, right now it might seem a little mysterious why we would offset the light source so that the events are simultaneous for Bob, but they're not simultaneous for Alice. That will come into more clarity in a minute as we do the derivation. And you might also be wondering, how do we know where to put this light source so that those photons arrive consistently? I'll show you that we can actually make that calculation to figure out where to put the light source, but if you'd like to kind of think about this operationally, like if you were to do this experiment, how would you know where to put the light source? Well, you could kind of do trial and error. You put the light source somewhere and see if Bob says that the photons arrive simultaneously. If not, adjust the light source location until they do, rerunning the experiment each time. And then once you're happy with the location of the light source that gives simultaneous events for Bob, then you just measure the location. And of course, we know that the events will not be simultaneous for Alice. So if you try by trial and error to locate the light source such that the two photons reach the walls at the same time in Bob's frame, what you will find is that the distance from the left-hand wall to the light source is not half of L prime, but rather a little bit more than half of L prime, and the factor by which it's more than half is the speed of light plus v, the speed of the train, divided by the speed of light. So you can clearly see that number is going to be bigger than 1. And what remains is a distance that's equal to L prime minus that value. So L prime over 2 times c minus v over c. And when you add those two together, you'll get L prime, the total length of the train. What we'd like to do now is confirm that in fact the two photons arrive at the walls of the train simultaneously. And we're going to do that by drawing the picture sometime later and seeing how long it takes each photon to make that trip. Once we've confirmed that those photon arrivals are simultaneous in Bob's frame, we're then going to go and reanalyze the same situation from Alice's frame to figure out what the time difference is between the arrivals of those photons. And now, and after we do that, we'll have a quantitative description of the delay between events in her frame. And that'll give us something really important called the rear clock ahead. What we're going to find is that when two clocks are moving at the same speed, like Alice's clocks moving through the ground frame, then if those clocks are not in the same location, they're actually going to have different readings at one instant of time for Bob. We're going to call that the rear clock ahead, and the whole point of this exercise is to derive that result. So what we need to do now is draw the second image in Bob's frame, and that is the image at the instant that the photons arrive at the walls. So let's see. I'm going to indicate the original location of the light with the green vertical dashed line. Okay, and I'll just draw that all the way down. And I'm going to do the same for the left wall. And I've moved this wall over a little bit. And the right wall has also moved over a little bit. We are making the claim that these two photons arrive at the wall at the same time. So in this diagram, both photons are hitting their respective walls at this single instant of time. And remember that this is Bob's frame, so Bob does not move in this frame. So he's still in the same place he was, and we'll just be really explicit about that by putting a dashed line showing that he has not moved. Okay. We can also indicate that the train continues to move to the right with a velocity v. We're going to need to keep track of time in Bob's frame, so I'm going to draw a clock, and the symbol that I'll use throughout this course for a clock is a little diamond. And here, imagine just a clock planted on the ground, and it's going to give us a reading. And the number in this diamond represents the reading on the clock. And we're going to start the clock at 0. So in the first picture, that's Bob's time of 0. And in the second clock, in the second diagram rather, we don't yet know the number on that clock, but it's going to be sometime later, t prime. So t prime minus 0 is the time interval, or the time elapsed, in Bob's frame. It's the time elapsed in Bob's frame between the launch and the arrival of the photon. Between launch and arrival of photons. Okay. Good. So now we want to, let's move this up here. Now we want to do a little calculation. We want to see how far does the left photon travel. Okay. The left photon has to travel, it does not have to travel the full length, the full distance between the light source and the wall, does it? Because the wall is approaching. So the photon doesn't travel this whole distance. It only travels this distance between these two vertical dashed lines. And as you can see, that's less than this purple value of L prime over 2 C plus V over C. So we need a way to write down a mathematical expression for the distance traveled, right? In words, it's this purple distance minus this bit here. Okay, so that we can make a label for that bit there, that distance. And notice that that distance is the distance that the left wall travels in a time t prime. Okay, well, the distance traveled is equal to a speed times a time elapsed. And the speed is v, and the time elapsed is t prime. Okay, so this purple distance here that we're labeling is just simply v t prime. Okay, and the quantity that we care about, which is the distance that the photon travels, well, that's just this space in here. It's the original gap between photon and wall minus the amount of distance that the wall traveled. Okay, so we can write that one out as the distance traveled is the total amount of the original gap, L prime over 2 C plus V over C, but we have to take away VT prime. So that's one way to write this distance. But there's also another way to write this distance, and that is by looking at the photon as an object that travels, right? It travels at the speed of light, c, and it travels for a time t prime. So this distance from where the photon started to where the photon ended, that distance is its speed, c, multiplied by the time interval t prime. So we could also write the distance traveled as c times t prime. And those two must be equal to each other. So believe it or not, we're done with the physics. We identified kind of the motion and expressed that algebraically as an equation. And now it's just turning the algebra crank to simplify this expression. And we're trying to solve for t prime, the time it takes the left photon to reach the left wall as measured by Bob. So we're just going to step through bit by bit, and we'll carry this one out explicitly each step along the way. The first thing I'm going to do is bring the VT over to the other side. And then recognize that I can just express that more compactly as C plus V times T prime. Okay. Well, on the left side, I can just rewrite the same thing that was there before in a way that makes it clear that we're going to be able to cancel the C plus V term on the left and the right side. And we're done. We have T prime expressed in terms of L and C. So I'll write that again, flipping the sides as T prime is equal to L prime over 2 divided by C. And just to be really, really explicit, I'm going to give this T prime a label because we're doing the calculation for the left going photon and for the right going photon. So I'm going to call this T left, meaning the amount of time it takes the left photon to reach the left wall as measured by Bob. Next, we want to repeat this same calculation, but for the right photon. So I'm going to shuffle things around a little bit, and we're going to play the same game. We're going to have to write down the distance traveled by the right photon, and we're going to write it in two ways, in terms of the photon speed times the elapsed time, and also in terms of the geometry of the picture. So notice that the right-hand photon starts on this green line, and it ends on this wall. So the total distance that the right-hand photon travels is the distance from the green line to that wall, which can be written by the original separation between the source of the photons on the right wall, plus the distance that the right wall moves in the time t prime, right? And we know from before that that distance is v times t prime. So we can express the distance traveled in two ways. We can express it as the speed of the photon multiplied by the time it travels, but we can also express it as the sum of these two purple terms. So we'll write that out. L prime over 2 C minus V over C. This time plus, instead of minus, Vt prime. Okay. And, we're going to play the same exact game, right? We're done with the physics. We're going to turn the algebra crank. So here we go. We're going to bring the Vt prime to the left, like so. And we're going to once again recognize that we can make it more compact by factoring out the t prime. And on the right-hand side, we're just going to express it as L prime over 2C, C minus V, once again recognizing that there's a term in parentheses that cancels left and right. Oh, I got a little bit ahead of myself, didn't I? Let me undo that and copy this down below. I'm trying to cancel two terms that are in different lines. We don't want to do that. We want to cancel terms in the same line. And then we are done. The time it takes the right photon to make the trip, according to Bob, is L prime over 2, half the length of the train, divided by the speed of light. And the important thing here is we're talking about the time it takes the right photon to make this trip. But notice the value for that time is exactly the same as it was for the left photon. So these two terms are equal. And what that means is we've confirmed that if we put the light source where we said it we were going to put it, not in the exact midpoint of the train, but offset from the midpoint, that does indeed guarantee that the photons will reach the walls at exactly the same instant of time. So Bob says the photons arrive simultaneously. Okay, so simultaneous being a synonym for same instant. Well, okay, I think now we're in good shape. We've confirmed that these two events in Bob's frame are going to be simultaneous, the two arrivals of the photons at their respective walls. Now we are set up to analyze the same situation, but from Alice's point of view, in Alice's frame. And what we're going to find is that the photons will not arrive simultaneously, but the difference in those arrival times will allow us to quantify how not simultaneous they are. And furthermore, we're going to learn something really interesting about the nature of the two clocks that we're going to put on Alice's train, one on each wall. Okay, so we are now geared up to repeat the same calculation in Alice's frame. So let's just make clear we're in Alice's frame, which is equivalently the train's frame. Okay, and in that frame, we're going to need to draw three pictures. One picture for the time of the launch, one picture for the time that the right-hand photon arrives, and one picture for the time that the left-hand photon arrives. Okay. In Alice's frame, we have Bob on the ground, and he's not at rest. He's moving. He's flying or zipping along to the left. And we have Alice on the train, and the train is stationary. I'm actually going to move this diagram over a little bit to give us more vertical space for three diagrams. Okay, so we still need to have our light source, right? And we need to recognize that that light source is not in the middle of the train. Instead, it's offset from the middle. And we also want to remember that the train length is L, not L prime, because we're going to allow for objects to have different lengths depending on their speed. And since we're in Alice's frame, which we call the unprimed frame, we're going to label the length using L instead of L prime. So there's no prime on the L. That's what we mean by the unprimed frame. And we're going to give little clocks for the walls on the train. Okay. Now we also need to remember that the light source was not in the middle of the train. Okay. If it were in the middle of the train, it would be at a location L over 2 from the wall, but it's not. We shifted it to the right And so it's a distance L over 2 times C plus V over C from one wall, and L over 2 times C minus V over C from the other wall. Okay, good. And we're going to start our clocks at 0, so we'll put a reading of 0 on these clocks. Okay, and we can call this event, this snapshot, is drawing a picture of the event photons are launched. Okay. Well, then we need to see what happens sometime later. And what we know is that both photons travel at the same speed. The right photon has to travel a shorter distance than the left photon. Remember, the train's not moving, so all the photons have to do is go from the source to the wall, and the walls are not running away or running towards. So the right-hand photon will arrive at its wall before the left photon arrives at its wall, because the right photon just has a shorter distance to travel. Both of these photons are traveling at 1 foot per nanosecond, the speed of light c. So the one that has to travel a shorter distance will do so faster. Great. So let's draw the same scenario at some time later. And in particular, we'll draw it at the time that the right-hand photon reaches its wall. Okay. All of this part is the same. The photon source hasn't moved, the walls haven't moved, right? Just to highlight that, we'll draw these dotted lines representing where the wall used to be and where it is now, and it's just a vertical line, nothing's moved there. The ground has moved, and so has Bob. Bob has shifted to the left. Okay, and we're going to label this time TR, because that's the time that the right photon hit the right wall, but the left photon is still in flight. Okay, but both of these clocks have the same reading. How do we know they have the same reading? Well, if we have two clocks and they're at rest, by definition, we're going to make sure that our clocks are in sync with each other. So they're starting at 0 and they tick in unison. 0, 1, 2, 3, and they tick all the way until they get to TR. And that is this instant that we're looking at right now. Okay. So we can say that the distance that this photon has traveled, we can express it in two ways. Okay, the first way that we can express it is already written here. It travels this distance, L over 2, C minus V over C. But another way to say it is we have a photon traveling at the speed of light for a time TR, and so the distance that it travels in that amount of time is simply given by C times TR. So let's look at this and write this out. If we see how long it takes the right photon to travel, we're going to equate these two expressions, L over 2 C minus V over C and C times TR. Those two are equivalent, and we want to solve for T, the time it takes the light to make the trip. So here we go. We're going to say C times TR is equal to L over 2 C minus V over C. And our goal is to solve for TR. And we can do so quite straightforwardly just by dividing both sides by C. And we have L over 2 C squared C minus V. Okay. So that's the time it takes the right photon to travel. Sometime later, the left photon will arrive, but we need a picture for that. Okay, so here's our third and final picture. We have the ground, we have Bob moving even further to the left now. And we have our train not moving at all, right? We're in the train frame, so it is at rest. Let me make some space for my clocks here. We got clock number 1, clock number 2, and our light source. And our photon on the left is now arriving. Okay. So we're going to call this time TL for the time that the left photon arrives. And I'm not drawing the right photon because it's already arrived, and once it arrives, it gets absorbed by the detector, and it no longer exists as a photon. Okay, so we can label each of these diagrams, right? The first one we said was photons launched. The second one is right photon arrives. And the third one will be left photon arrives. And these are all as observed in Alice's frame, in which Alice on the train is at rest. Okay, well, we can play exactly the same game that we've done before, right? We're going to have two ways of expressing this distance. One way is given here, L over 2, C plus V over C. That's just how far the photon had to travel to hit the left wall. But we also know the photon is traveling at the speed of light, and so we can also write that same distance as speed times time. And this time it's C times TL, because between the starting point of time 0 and the ending point of TL, that's how much time has elapsed. C times TL minus 0. Okay, so finally we're going to say our left photon. We have CTL is equal to L over 2 C plus V over C. We simplify and solve for TL by dividing both sides by C again, and we have L C minus V, C plus V over 2C squared. Okay, and if you compare these two terms, it should be clear that the left time is bigger than the right time because the L2 and C squared are the same, but the numerator here has a C plus V, which is going to be bigger than the C minus V. So we have two results. One is that TL is bigger than TR, which means the right photon arrives first. But we also have this really important second result, which is now that we have mathematical expressions for the time it takes to go for the left photon and the right photon to arrive, we can do more than just say which one arrives first. We can say what is the time difference between them. So we can actually calculate the time difference. All right, and we'll do that on the next page. Okay, so recall from the previous slide, we had determined that the left event happened later than the right event. Therefore, it took more time for the left photon to arrive than for the right. So TL will be bigger than TR. And we had these two specific expressions for TL and TR. So we now want to calculate the difference in these two times, TL and TR. Okay, so we're going to look at time difference. And we'll just write that as TL minus TR. And we have expressions for TL and TR. We have TL is nothing but L C plus V over 2 times C squared. And TR is nothing but L C minus V over 2 times C squared. Okay. So here we're just turning the algebra crank and simplifying. Notice that there is an L over 2C squared in both of these expressions, so we are free to factor those out. And then we're left with C plus V and C minus V inside. Okay. The next thing we'll recognize is that we have here C plus V minus C minus V, quantity C minus V. So that's minus C plus V after you distribute the minus sign through the two terms inside. So we have the C's canceling, but we get 2 times V. And when we simplify that, we get the cancellation of the 2, and we're left with LV over C squared. So TL minus TR, the difference between those two clocks readings is L times V over C squared. And we're going to write this in a slightly different way, which is to say that TL is equal to, I said TL and I wrote TR, didn't I? TL is equal to T right, T left is equal to T right, plus LV over C squared. Okay, and just to be clear, this is left and right. This result is a major result. What it tells us is that the left clock and the right clock have actually different readings on them when the photons reach the walls. And the amazing thing is that in Bob's frame, remember, the photons reach the walls at the same time. So photons reaching walls for Bob is one instant of time. And in that one instant of time, these two clocks on the train have different numbers on them. Okay, and how different are the numbers? Well, it depends on the length of the train and how fast the train is going. So what we're gonna do is give this a name. This is going to be one of the three main results of this class for relativity. And we're going to call this the rear clock set ahead by LV over C squared. And my students a few years ago decided to give this a nickname, so they called this the RCA for rear clock ahead. We are going to see the RCA over and over and over in this course. Okay, so we'll often say things like rear clock ahead by LV over C squared. And what that means is the rear clock is bigger than the front clock by an amount LV over C squared. And now we have to understand what do we mean by rear clock. Okay, and just as a point of clarification, rear and right are different things. Right? In the problem that we just did, the left clock is the rear clock. So on the final slide here, I'm just going to spend a few minutes explaining how we know which clock is the rear clock and what we mean by rear clock. Okay, so we have all the pieces. Now let's put all the pieces together to tell the final story. Right? And we're going to do this in Bob's frame. All right, and in Bob's frame, recall that by design, the photons arrive at the same time. So we have the train, we have the ground, and we have Bob. And we know that Bob's at rest and the train is moving. Okay, and we have this light source that was offset from the middle of the train. And we have, remember, both photons in this frame arriving simultaneously. Okay. And Bob has a clock that he was keeping track of time with. But in fact, Bob's got clocks all over the place in his frame, and they all are at rest relative to him, relative to ground, and relative to each other. And they all read the same thing. Clocks at rest, they all read the same thing in his frame. And we decided that we were calling these T prime. So for Bob, TL, the time the left arrived, TR, the time the right arrived, were equal to each other, so we just called it T prime with no subscript. Okay. But that was not the case for Alice's clocks on the train, right? When the right photon arrived, Alice's right clock read TR. When the left photon arrived, Alice's left clock did not read TR, it read TL. And TL was bigger than TR. Okay, so what this all comes down to then is that in Bob's frame, all of his clocks have the same reading, and at that instant, Alice's clocks do not have the same reading. One reading, TL, is bigger than the other. Okay, and what we said specifically was that TL was bigger than TR, and more specifically, TL was equal to TR plus LV over C squared. Okay, and we called that the rear clock ahead time. Okay, so what do we mean by rear clock? Okay. Well, look at this train. This train is moving across your screen from left to right. From Bob's point of view, the train used to be over here. The first clock that got to Bob was the right-hand clock. The second clock that got to Bob was the left-hand clock. So we're going to call the rear clock nothing more than the clock that gets to you last. So the rear clock is the one that gets to you last. Or in this case, the one that got to Bob last. Okay, so in this case, that's the left clock. Okay. But if the train had been going the other direction, then the left clock would have got to Bob first and the right clock would have got to Bob last. And so the rear clock would have been the right clock. So there's nothing intrinsic about the front clock and the rear clock. It depends on the direction of motion of the object. In this case, the rear clock is the left clock. Okay. Now, we talked a little bit about different lengths and so on, and this rear clock ahead has a length in it. Well, which length are we talking about? Is it the contracted length of the moving object, or is it the rest length of the object? Well, remember, we had L and L prime. L prime was the length of the train in the frame where the train was moving. That's Bob's frame. But this equation, you hear my son running around in the background. This equation does not say L prime. This equation says L, okay? And indeed, this is the rest length. This is the rest length of the train. It's the length of the object in the frame where it's at rest. Okay, so that's the length that Alice would say the train has. Okay, so now let's see the rear clock ahead in action, okay? So let's imagine we have a train frame, or we're looking at the train from the train frame, okay? And in that frame, the train is at rest. All right, it has a length of L. And the clocks are going to start out reading 0. Sometime later, the train is in the same place, right? Remember, the train doesn't move. And let's say this is 1 second later. Well, now both clocks will advance by 1. So the clocks have the same reading as each other. And then we wait, one more second. And now the clocks read 2. So one key idea here is that clocks at rest have the same reading. Okay, and the train clocks are at rest in the train frame. What about in the ground frame? Okay, in the ground frame, we have 2 clocks that are moving, and what we saw is that their readings will not be the same. Okay, so these clocks are moving. Let's say they're moving to the right with speed v. And this length is not L, but it's L prime. Okay. Well, let's say the reading on the front clock is 0. Okay, and I know it's the front clock, right? Because if you're standing over here, this right-hand clock is going to get to you first. So this is the front clock, and this is the rear clock. Well, if the front clock reads 0, the rear clock is not going to read 0. It's going to read 0 plus LV over c squared. And notice it's L, not L prime, but it's the rest length L of the train. Okay. Sometime later, this whole system shifts to the right. And let's say it's 1 second later. So the clock that used to read 0 is now going to read 1. Okay. And the clock in the rear is still going to be LV over c squared more than the front clock. So now the rear clock is going to read 1 plus LV over c squared. So notice that both clocks have advanced by the same amount. They've both advanced by 1. And also the rear clock continues to be LV over c squared ahead of the front clock in both cases. Okay, great. One other instant of time later. Let's say 1 more second later. Now the front clock reads 2, and you bet the back clock reads 2 plus the rear clock ahead, LV over c squared. Okay, so this is how those clocks are going to advance as time goes on, and of course we're continuing to be in the ground frame, so in all 3 of these diagrams the train is moving to the right. Good. So key ideas are, number 1, both train clocks advance at the same rate as each other. Point number 2 is that the rear clock is always ahead of the front clock by LV over c squared. And a third key point is that if you increase the speed and or you increase the separation between the clocks, then you're going to get a larger time offset between the clocks, because that time offset is proportional to the separation between the clocks, L, and it's also proportional to the speed that the clocks are moving. Okay, take a breath. Whew! There was a lot in this video. This is the first time we had done a fairly quantitative calculation, but pat yourself on the back, because there are 3 main consequences of special relativity: rear clock ahead, time dilation, and length contraction. And we have just derived in all gory detail the first of those 3. So you've basically done a third of the content of special relativity, at least for those 3 consequences, okay? So you're in great shape. If there were pieces of this video that didn't sit well with you or that you were unclear on, by all means go back and take a look. And additionally, on the website, I will provide you with practice problems to make use of the RCA. All right, and we will be practicing this a lot throughout the semester. Take care and talk to you next time.